Yeah, cool. So, congratulations on almost completing the math behind AI, right? The course is basically designed uh, as an introduction to the world of AI, right? And in that, I have taken the most basic model that usually uh, you need to understand, right? If you want to enter the world of AI. However, linear regression is not something that is only used for teaching. Okay, even today, many of the companies they use linear regression model for a particular reason. The best part about linear regression is, say for example, I have written something like this. If this is the final line I'm fitting, right? Say for example, 3x1 plus 2x2 minus 3x3 plus some constant, maybe 6. If this is my final line, this is not a univariate function, is it? It has three separate features. X1 is one, x2 is two, another, and then x3 is another. And generally in the real world, this is how it is. Anything you want to predict, you will require multiple features. Okay, because many things are affected by multiple influencers. For example, uh, if you want to say measure someone's health, correct? Then to maybe we found a metric to quantify it. Let's assume how healthy a person is. Okay, then we know that a person's health index is not something that you can just say, right? It is affected by multiple things. What is the weight of the person? What are the eating habits, right? And then maybe height and weight, maybe we can include here. And then is there any genetic condition, right? And then maybe some uh the habits, right? Lifestyle, correct? There are multiple things that affect a person's health. It is the same thing with anything. If you want to predict a person's marks, right? Then again, marks, if this is something that you want to predict, if this is y variable, then obviously there are things like how the hours spent on studying, right? And then maybe the absorption capacity, how much of whatever you learn, how much you can absorb, right? Absorption capacity, and then again memory capacity, and again how about the validity of the notes that you are studying. You may study something really well, you may remember everything, but what if the notes themselves were wrong or not sufficient enough? You obviously will not get good marks, right? So in real world, wherever you go, no parameter is dependent on just one single feature. It requires multiple features. Okay, and based on those features, how much each feature is important is a different story. Okay, but there are multiple factors that affect a parameter. So in such situations, how does our linear regression model do this? Yesterday we saw for as univariate function, it was like y is equal to wx plus some bias b, correct? Because it had only one feature. Now, when there are multiple features x1, x2, and x3, how each feature is affecting the change in y, that we need to calculate. That is how it is calculated. Okay. In the background, whatever we learned yesterday, the same process goes on, but for every particular feature. Okay. Now, what are these 3 plus 3 plus 2 and minus 3? These are the weights that have been assigned to x1, x2, and x3 respectively, right? Correct. And this 6, the bias is applicable for all of them. It is a general term, right? Now, the advantage of linear regression is that looking at the weights, right, it will give you an insight how varying some feature or how can I control the output y by varying any one of these features? This is what we can understand from the linear regression model. How, what can you say? If I want to increase y, right, then I can increase x, then also y increases, right? I can increase x2, then also y increases. But to increase y, I need to reduce x3 because it is minus, right? It is subtracting from the total value. So if I want to increase y, then I will have to decrease x3, correct? So how each feature is related to y, whether it is positively affecting or negatively affecting, this insight can be drawn using the linear regression model. Make sense? Yes? Just give me a second. Yeah, sorry. Okay, I hope you were able to understand what is the advantage of linear regression, right? How by tweaking any one of the features, I can manipulate y, my outcome. If I am talking about the company's revenue, then X1 could be employee expenses, or sorry, X3 could be employee expenses or expenses of the company, right? X2 could be maybe sales of the company, and X1 could be maybe some contract the company has for services, right? Anything is fine. Now, if I want to increase the revenue of the company, I will have to increase the service revenue. I will have to increase the sales revenue, but I will have to cut down on the expenses, right? So in this way, the model becomes more explainable. So if you are an employee, or say you are a branch manager of a company, you need to talk about some metric or some plans towards increasing the revenue of the branch to your higher company's board of directors, maybe, right? Then taking a linear regression model on your company's numbers would really help you to explain it properly. Correct? That is the advantage of linear regression model, and that is where its usage still exists. However, if you are looking for some really serious AI engines, the LLMs and other things, right? Generative GANs and other things, then linear regression may not be used or is not directly used as it is. Some modifications are there. There are some improved models. Those things are used generally. Okay. So please keep that in mind, because most of the models that are advanced, you don't know what is happening inside. But for linear regression, you can see everything that is happening inside the model. Okay. However, if you really want to implement a good regression, linear regression model, then the linear regression requires basically 5 assumptions to be true, or you can say 5 validations on the data. Only if all 5 are met properly, at least to some reasonable degree, then we can say that this particular linear regression model is something that we can use in the real world. Okay. And let me talk briefly about them. I will not go very deep because this itself is a topic to, explain in maybe 2 to 3 hours. But basically, I will give you what the idea is. Fine. The first assumption is called linearity. What do you mean by linearity? It means the features are linearly related to your target. Okay. If I draw a feature over here and then the target over here, the y and x, right? Then the plotting of values for a particular x value, what is the value of y? In that way, if I mark the points, if they are somewhere like some randomly distributed like this, right? We don't know how they are related, right? In this situation, you cannot use LR. Impossible. Doesn't work. Okay. So if you want LR to work, then it should be something like the values are distributed like this, maybe, right? There is a trend that is being followed, that here what is happening, as x value is increasing, y value is actually coming down. This is what, if you looked at the what is that correlation, then this is negative correlation. Or maybe something like this. Even this is also valid. Something like, right? The data is moving in this direction. This is what? Positive correlation. This must be there. Okay. This is the first assumption. Otherwise, you can't fit any line anywhere, right? That follows a trend, because ultimately, when you want to fit a line represents a trend, and there should be a trend in the data that the line can try to predict. That is the requirement. So that is why this part, the linearity concept, it has to be satisfied. The second important thing is called no auto collinearity, we say. Okay. What does it mean? Auto collinearity not present. This is the requirement. Please understand. Okay. What does it mean? It means that every row in the data, right, should be independent of each other. Means my second row is not dependent on first row, or maybe any row that is before it. Okay. So these things actually happen in something called a time series data. Time series is what? For example, I can take the example of temperature. Generally, the temperature of today is dependent on what the temperature was yesterday, correct? Or maybe some share market data, share value depends on yesterday's value, right? All these kind of data you cannot use for LR. Doesn't work. Okay. This is another observation. Auto collinearity doesn't exist. Means what? Rows are independent. Makes sense? Why doesn't it work? Because the dependency of a row on its previous ones, the model cannot learn it. It doesn't work. Because when you are trying to predict, right, you are simply passing a particular feature set of a random some random values that represent as a row, right? You don't have the previous rows, you don't have the rows after. One single row you pass as the input. If there is a relationship of an input for with respect to the previous ones, you don't have them. Your model doesn't capture it. That is why it doesn't work when you have auto correlation. Okay. I mentioned auto collinear. It's actually correlation. Correlation of the data with itself. Okay. Next, let's move on to the third assumption. The third one is actually officially called as homoscedasticity. Okay. Means what? Constant variance of errors. Okay. What does it mean? It means my model predicts y cap for a particular x, right? Now, if you plot out this y cap, right? How do you calculate the errors on your test data set? You do y minus y cap. This is what gives you an error, right? If you plot these errors, or if you calculate the variance of this error, it should be constant across the graph. Okay. So what does it mean? It means your model makes almost equal mistakes over the trend. Say, for example, I have something like this. I am plotting errors for certain values of y, right? My errors are like this. They are rising, right? What does it mean? At lower values of y, it works nice, okay, acceptable. But as the value of y increases, my errors are increasing. Means what? The model is bad. So for higher values, say for example, I am trying to predict the um, say predict the house values. Okay. Y value is lesser means what? It is cheaper houses. Y value is higher means what? Expensive houses. If the errors are going up like this, means what? My errors, my model is making too many errors, or the error that the model is making for higher valued houses is more compared to cheaper houses, right? Means what? I cannot use this model anymore, at least for higher valued houses, right? That is the third assumption. It is called official name means what? It is the mathematical name that is given homoscedasticity. Okay, it is basically nothing but the constant variance of errors. In this situation, if this is satisfied, the errors should look something like this. For different y values should be something like this. Okay, all these points are errors. They are spread out in a straight line. Understood? This is 3. Fourth assumption is called normality of errors. What it basically says is, if I plot out the errors, only the errors, and with respect to count, how many number of errors, okay? If this is the case, then it should look something like a bell curve. Okay, what does it mean? My errors are distributed in such a way that I'm making fewer and fewer mistakes at these ends. Means what? At extreme values, right? Extreme errors are very less, and most of my errors are within a particular range. They are concentrated. Okay. This is something that has to be there. And then last one is called multicollinearity. Okay. Multicollinearity should not be present. What does it mean? It means the features should not be related to each other. So, say for example, if a person's height goes up, generally his weight also goes up, correct? Or if employee count goes up, salary expense also goes up, right? Basically, these two are following the same trend, correct? Here also, the same trend. In such situations, if these two are called x1 and x2, then while predicting, the model doesn't understand how much weight to be assigned for x1 and how much weight to be assigned for x2, because you cannot calculate the weights independently. Increase in x1 also results in increase of x2. Increase of x2 also results in increase of x1. And how much weight should be applied? That is the problem. You do not get any errors while programming, but your model doesn't explain anything properly. What is the basic requirement? You should be able to explain the contribution of independent each feature to the target, right? This was the requirement. But what if x1 and x2 are dependent? Or dependent in the sense they are related to each other. So increasing in x1 also increases x2. Okay. Then I cannot independently increase x1 and expect some quantified increase in y. Okay. If x1 and x3 are related, they have exactly opposite weights, right? That means what? If I increase x1, x3 also increases, my y doesn't increase at all. Make sense? That is the issue with the multicollinearity. This should not be present. Generally, how do you calculate this multicollinearity? You just draw a covariance matrix, okay, where you feature 1, feature 1, feature 2, feature 2, feature 3, feature 3, feature 4, feature 4. In this manner, you draw a covariance matrix, okay, and try to find out how much covariance is there between F1 and F2. You write this here. Suppose I have some 0.95. Obviously, the diagonal elements will have 1, right? It is with respect to the same feature. So these are 1. We just ignore it. Now F1 versus F3, say for example, I have 0.04, very less correlation. F1 and F4, I have minus 0.7 maybe, correct? Now in this case, if I take this as an example, then out of F1 and F2, I can keep any one of them. I should keep any one of them because essentially they are following the same trend. 0.95 correlation means what? They're exactly the same, right? So I should ignore any one of them and keep the other. Generally, that is what we do. Okay. However, F1 and F3 do not have any relationship per se because the correlation is 0.04. Then we can keep F1 and F3. No problem. They are independent features contributing to the outcome independently. Okay. F1 and F4, they are negatively correlated. Means what? they are following almost the same trend in the opposite direction, right? Then also we should ignore any one of them. Which one to select is called those all those things, they come under the concept or the work called feature engineering. It's a huge part in any data science profile. You need to engineer which feature to keep and which feature to drop. Okay, so these are the 5 assumptions. I have just written a sample code. I already have it ready just to show you how it looks like. Okay, don't have to code it anyway. Let me share the collab. Is there any doubt regarding this? If you have any questions, you can ask before I switch my screen to collab. No, no doubt? Okay. I hope my screen is visible. Okay, nice. So I have loaded this data set from Seaborn MPG. Okay. This data set basically talks about the relationship between miles per gallon, the mileage of your car with respect to number of cylinders, the displacement, horsepower, weight, acceleration, model year, and origin. All these things are there, and which model it is. This is the data set that we have. Okay. So using this data set, I actually did fit a linear regression model. If you look at this, I am not coding it like we did, right? There is a linear regression model available in sklearn, scikit-learn. Okay, I'm using that I am simply fitting the model. Cool. If you look at this data, don't worry if you don't understand it, it's fine. Just get the idea what I am trying to do. So here I have loaded the data set into something called DF. Then this X is what my features are: cylinders, displacement, horsepower, weight, and acceleration. And what is my target variable? MPG, miles per gallon. Okay, I have separated them from the data frame. So Y now contains this column, this one, and X contains all these columns till maybe here, till here. Do we have here? No, we don't have here as well. So till here, these are the features. Okay, is it visible to you guys?
Yes, sir.
Okay, nice. Right. After that, once I have split the data, right, into the features and the target variable, then I will for training and testing. Generally, this is how we do to work with what data we already have, right? To build the model, we need some data, and with that data, we will have to divide them into two parts. One part is used for training, another part is used for testing. The general rule of thumb is 80-20 split, where 80% of the data you use for training, 20% of data you use for testing. Okay, there is a function that can do it for you. However, here what it does is it randomly picks 80% of the data and puts it in X-train, and randomly picks remaining 20% into white train. Sorry, remaining, yeah, randomly picks 80% in train part, and then remaining 20% in test part, X test and Y test. Okay, this random state, it is used just to give you a seed value, so that every time you run you will get the same output. It's a part of the random function, don't worry. Then fit the model, right? We need to instantiate the model for linear regression. Just 2 lines, you got your linear regression trained. This is how it is done in the industry. You don't have to write the entire code. However, your advantage is that we will look at your advantage later. All right. So we fit the model means what? We trained the model. Now we need to predict, right, based on the test. Voice is not clear, is it? Just give me a second then. Is it audible now? Yes? Fine. Right. What I am trying to do, I am just now, since I have fit the model using X train and Y train, right? Now I am trying to predict based on the X test. This is Y predicted now. Okay, how do you calculate MSE, mean squared error? There is a function. Again, it is the same thing. Whatever function we wrote, the for mathematical formula we wrote yesterday, or day before yesterday. It is the same thing, but it works for multiple values. That's all. So we calculated MSE, y test, comma, y predicted. We have passed them. It returns the MSE value. R square, again, there is a function. We are making use of that. Fine. Then I'm printing them just to show you the assumptions, right? I am printing these parts. These are part of the plotting set. So let's run this. If you look at this, R square 0.6485 means what? 64.85% of the data that is present, my model can actually explain. Okay. But if you look at this, why is it that bad is, look at this, predicted MPG and errors. What is this part? Which of the assumption is it? Can anybody tell which of the assumptions is connected with this plot? As the value of y is increasing, the errors are plotted. So if you look at this, my errors are not having constant variance, right? For higher valued cars, my or efficient cars, my model is predicting very badly. Look at the errors. They are spread out like this, right? Somewhere around here, it is okay in this much section, right? Even for very high fuel consumption or less least experience, least efficient vehicles, comparatively bad. Can you see this? So our homoscedasticity requirement not satisfied in this particular data set, right? The same thing is applicable for another thing. Look at this. Look at this chart. This one. What's happening? Residual value means what? It is errors. Errors are not centered around zero, right? The chart is essentially skewed to the left side. I hope you remember these things that I had taught in the previous classes, right? This is not following the proper normal distribution. So this is which one? Normality of residuals is not satisfied, right? And let's look at the other one too. There is one more plot here. Can you see this? Yeah, look at this. Cylinders, right? And displacement, horsepower, weight. So as the number of cylinders increases in a car, the engine becomes bigger. So based on that, obviously you will have more displacement power that is there. Even horsepower increases, weight also increases, right? As the weight increases, acceleration decreases, correct? So all these things are correlated to each other. Can you see this? So means what? The data that I am trying to use for this particular linear regression model doesn't fit. We can't use it just as it is. We need to work on the data. There are many pre-processing steps, or we need to drop some of the features. After that, maybe I will be able to fit a proper linear regression model, then make use of it. Okay. Just to give you a gist, I am synthesizing another one more thing that you should always remember is you cannot find a perfect data set in real world. It doesn't work. Things are always dependent on each other. Okay. So for the most part, the multicollinearity last assumption is the hardest thing to get. Okay. Remaining things we can somehow manage. So I will run this code. It is a different data set. Obviously, I'm just synthesizing. Okay, because unless you synthesize, you can't get them in reality for 100% assurance. So if you look at this now, predicted values and versus errors, look at the errors. They are spread out, correct? For this negative error, large error, there is somewhere around here, there is a large error that can compensate. So with that, I will ultimately reach to this particular variance, center line. Okay. So this particular thing holds. And then the other one, residual value, the normal distribution thing, right? Look at this. The highest values that the model is making uh, zero error, correct? For most of the readings, then it is distributed in a normal curve. Some variations are allowed, that is okay. But if you look at the density curve, it follows almost the normal curve. Fine. And then look at this one. the multi-collinearity thing. No features, feature A, feature B, and feature C, none of them are dependent on each other in any way. Correct? So for that reason, if you look at the R square score, it is 0.9780. So my model can explain 97.80 of the information in the data. So a really good, great R square, right? Which you hardly get, or I don't think you will ever get this R square score in any real data set. Doesn't. You won't. So getting something around maybe 75% or 85% is it's like a greatest achievement. Okay. If you have any doubts, you just ask. This was more like giving you an idea how linear regression is used, what are the requirements, when you can use linear regression. All these things, I am planning to make a new course, an intermediate level course, where we will actually talk about all these assumptions separately, and then how to treat them, how to take a data set and use treat the data to meet these assumptions, and then what are other some really nice models that are available which do not depend on these assumptions at all. They are also there. So those things, I am planning to make a new course on that. For this level, it is this much is good enough for you, right? If you have any doubts, you can ask. Shall I stop sharing the screen? Yeah. So if you don't have any doubt, yeah, Jyotika Gowda is typing nothing. So how was the course? Can any of you just give me a direct feedback? Anyone? Maybe. So Niriksha, how was it? Was it worth your time? Yes, sir. The course is very helpful. Okay. Did you know about these concepts before? I knew few of them, but not detailed way. Okay. Hmm. So what about Deepak? Deepak Deshpandari. You were very regular to the class, right? Okay, Vandita is asking, sir, can you explain heat map once more? I will. I will. Hmm. Srishti Naik. Srishti Naik is from, I think you are from JMJ College, right? So how was the course? Vinuta, Rajeshwari, Jyotika, Prarthana, Ananya. Okay, Sharat said many things. In our syllabus, we have very basic Python syllabus. I learned something new, and this is my first course as the recorded session is helpful for me. Nice, good to know. Classes were really helpful, but it felt like it ended a bit early. If you feel like it, you can always join for the intermediate level, right? Mm. Nice. So, guys, I just in the afternoon I shared a feedback link. Ah, one thing. Yes, correct, correct. Vandita had asked the heat map thing, right? Heat map is a different graph in itself, but here in our code, we are using it for correlation matrix. Okay. What is happening here is, okay, this is the feature A, feature B, feature C, each row, right? And feature A, feature B, feature C. The correlation of feature A with respect to feature C is drawn here. It is 0.01. Okay. And correlation of feature C and feature B is drawn here. And with feature C itself is drawn here. Here you can see it is color graded. So darkest red represents full correlation like 1. Okay. Dark blue represents -1 correlation, negative correlation. And this one, right, 0 is lighter in color. This is what a heat map does. It depending on the value, highest value, least value, and middle value, it assigns a color grading. This is something to do with the plotting feature, right? SNS. The Seaborn library has this particular plot. And for that particular thing, we are making use of for plotting our correlations, we are making use of this heat map. If this one has no almost no correlation, none of the features have higher correlations, right? But if you come back to this one, here you can see, look at this. The darker red ones, 0.95, 0.95. It is the correlation between displacement and cylinders. The same thing gets repeated in the other half of the matrix as well. Okay. The bottom half is exactly similar to the upper half. I hope Vandita You got your, I was able to explain what you wanted to know. Yeah. How to draw this? It's essentially just this. SNS, pass the data. Then this C map is for color mapping, which color you want. I'm using cool warm. Cool represents blue color, warm represents red color. Okay. And then what is the minimum value? What is the maximum value? All these things. Annotation, annotate equal to true means what? I just asked you to write these values inside the boxes. 1.95.84 like this. Just search for seaborne heat map. You will understand. Okay, any other doubt? Sharath Padikar, are you typing something, man? Any other doubt? Jyotika Gowda is typing something about three assumption. Homoscedasticity. Okay. Hold on. Yeah. So you're talking about which one? Homoscedasticity, right? So here, generally what happens if you do not have a good data, or if your data itself is left or right skewed, then when you try to say, for example, your data is uh, increasing like this, x and y. If I take this as y and this as x, right? Say for example, I have an exponential relation between these two. Unlike having a linear relationship, right? Data being something like this, I I have something that looks like this. Data is distributed in this manner, okay, and it increases in this manner. Now, as you can see, it is more like an exponential relationship. If you write an x square function, then it actually looks like this, correct? However, in these kind of relationships, if I try to fit a line, a straight line, the line will be something like this. Straight line, right? We have to fit a straight line. What's happening? Around these 2 points, or between these 2 points, right? My model is predicting pretty well the errors here with respect to original y and my predicted y are comparatively lesser, right? So between these 2 points, the variance of my errors are comparatively same, almost same. Can you understand this? The spread of the data, the y values around this line, right? If I calculate the errors, then between these 2 points, the errors are having almost constant variance. So if I write y here and then error here, then between some 2 points, my variance value is going to be flat, a constant value somewhat. That means what? The data is spread something like this. Is following. Data is what? The error values. Correct. Now, if you look at this part, the bottom one, this area and this area, here my line is predicting badly, right? Y value is moving away in this direction, the original Y value, but my predicted Y value is along these lines. Now the errors are increasing, right? And here also the errors are increasing. Here my model is over predicting, right? The original value is lesser compared to Y, or sorry, here it is actually under predicting, right? Here also it is doing the same thing. Makes sense? So the errors are more now, the variance has changed, the spread of data changed. So the variance, if you look at the errors are going to be something like this, right? Here also they are spread out in this manner. Some are positive, some are negative. So data essentially follows, the errors follow this trend. They are something like this. Correct? If you look at the variance from 0 point to the later points, if you go along the y-axis, now the variance, if you plot it, it will look something like this. Why? Because the variance is more here, data is more spread out, right? Here it is not that much, not that spread out. Here also it is more spread out. So the variance has to increase now in this part, right? Instead of getting a variance that is constant throughout, I am getting a bowl shaped variance in this example, which is not good for me. Okay, this is the homoscedasticity assumption. Understood? Here, what is happening for this particular part? My model is working really good. But for the other part, that whatever is left out, these two, the model is extremely bad. Done? Okay. Any other doubts? If not, by the way, this additional part is not recorded. Okay. This part I forgot to put it on recording again. Okay. If you don't have any other doubts, then I will close the session. Like I said, tell your friends if they are interested, ask them to join, and do not forget to give the feedback. Right? Good night. You're welcome. Yeah, you're welcome. Yeah, thank you. You're welcome. You guys can drop from the meeting.